Good morning. Today I will present the paper titled Algorithms for Advanced Packet Classification with Ternary Cams. This slide explains how TCAMs are used in packet classification. Routers classify packets using access control lists or ACLs, where each rule checks header fields such as protocol, source IP, destination IP, source port, and destination port. The search key shown on the slide is built from these fields. In the figure, the control plane manages the rule table and loads it into TCAM, while the data plane processes incoming packets. The packet processor extracts the header, sends the search key to TCAM, and receives the first matching entry. TCAM is powerful because it supports 0, 1, and X, where X means don't care, and it searches all entries in parallel. Modern TCAMs can support very high search rates, but their capacity and cost make efficient use essential. This slide introduces the two main problems addressed by the paper. The first is range expansion. TCAMs cannot directly store numerical ranges, so a range must be converted into multiple prefixes. For a W bit range, this may require up to 2W minus 2 prefixes. For 216 bit port ranges, the worst case becomes 900 TCAM entries for only one rule. The second problem is multi-match classification. A standard TCAM returns only the first match, but security and accounting applications may need all matching rules. The table supports the importance of this problem. From 1998 to 2004, the total number of rules increased about 5 times. Single range rules increased significantly, and the unique ranges also increased. So, range expansion becomes worse as databases grow. DIRP stands for Database Independent Range Pre-encoding. Its first idea is to represent ranges using general ternary strings, not only traditional prefixes. Its second idea is to use unused TCAM bits for this encoding. The table shows fence encoding. In this encoding, the value I is represented by I ones after a sequence of zeros. This structure makes it possible to represent any closed range using one ternary entry if enough bits are available. The theorem states that 2 to the power w minus 1 bits are necessary for worst case expansion of 1. The figure explains the practical version. Instead of encoding the whole field at once, the field is split into chunks. Each chunk is fence encoded, and the range is represented through a multiple try view. This reduces expansion while using a limited number of extra bits. This slide shows how DERP forms TCAM entries and search keys. In the first algorithm, if the start and end of the range are equal, it simply returns the encoding of that single value. Otherwise, it finds the split chunk, which is the first chunk where the start and end values differ. Then it creates an entry for the middle part of that split chunk. If the split chunk is the last chunk, the algorithm stops. If not, it adds entries for the part greater than or equal to the start value, and then entries for the part less than or equal to the end value. Finally, it returns all. Page 2 generated TCAM entries. The second algorithm is simpler. It splits the incoming search key into the same chunks, applies fence encoding to each chunk, concatenates them, and uses the result as the TCAM. This slide summarizes the evaluation of DERP. Table 5 compares worst case expansion for a single range field with 1024 ranges. With no extra bits, both DERP and region based encoding have a worst case expansion of 30. But as extra bits increase, DERP improves faster. With 8 extra bits, it reduces the expansion to 15, and with 44 bits, it reaches 7. Table 6 shows results on a real life database with 215,000 rules. Even though DERP is database independent, it performs very close to and sometimes better than database dependent region based encoding. The two graphs show the practical benefit. With about 32 extra bits, a real database can store about 50% more rules, and a random database can nearly double its capacity. Now we move to the second problem, multi-match classification. The goal is to find up to k matching rules with the lowest cost, not just the first match. The multi-match degree M means the maximum number of rules that can match the same key. Figure 9 shows an example where one search key matches 3 rules. Figure 10 shows that in real ACLs, most databases have a multi-match degree of 4 or 5, and the maximum observed value is 8. Earlier solutions have limitations. Entry invalidation disables the found entry and searches again, but it changes TCAM state and is not suitable for multi-threaded systems. Geometric intersection has high throughput, but it creates very large TCAM expansion, sometimes 25 to 100 times more entries. MUT stands for multi-match using discriminators. The core idea is to add a discriminator field to each TCAM rule, usually encoding the rule index. At the beginning, the discriminator is fully masked, so the whole TCAM is searched. After the first match is found at index I, the next searches only consider entries with discriminator values greater than I. Line by line, the algorithm initializes a list of discriminator prefixes. While the list is not empty, it pops one prefix, searches TCAM with that prefix and the packet key, and checks the result. If there is a match, it records the rule index, generates new prefixes for the remaining range after that index, and pushes them back into the list. The example shows that after a match at 0101, the next prefixes are 11x and 1xxx. This slide presents optimizations for MUD. The first optimization is mask-based discriminator assignment. Rules with the same mask can share the same discriminator because only one of them can match a given key. This reduces the required discriminator bits from log base 2 of the number of rules to log base 2 of the number of distinct masks. In the real 215K rule database, there are only 1,694 masks, so 11 bits are enough. The second optimization uses derp to encode the range greater than j in the discriminator field, reducing the number of searches. Table 8 shows that more derp bits lead to higher link speed. The method supports multi-gigabit rates, does not expand TCAM entries, and remains suitable for multi-threaded packet processing. To conclude, the paper presents two algorithms that improve TCAM-based packet classification without requiring hardware changes. The first algorithm, DERP, reduces range expansion by using extra TCAM bits and database-independent encoding. It improves worst-case behavior, scales well with many ranges, and supports efficient incremental updates. The second algorithm, MUD, solves the multi-match problem by adding discriminator fields and using masked searches to find later matches. It avoids per search TCAM state, so it works well in multi-threaded environments, and it does not increase the number of TCAM entries. Both techniques rely on unused TCAM bits, and they can be combined by allocating different extra bits to each method. Overall, the paper shows that smart encoding can significantly improve TCAM